Welcome to this lecture on air transfer and the part of air transfer that is governed by the wind pressure that acts on our buildings. And also this lecture will end with one of the exercises that we have also, where I'll demonstrate a little bit of that exercise we have. So we have wind around our buildings, so the wind is coming in on a facade of a building, and it creates an overpressure there, and an underpressure on the leeward or the back side of the building. So that's what we have some methods to estimate how much are the pressures in those locations. And this is governed by Bernoulli's equation that kind of turns the velocity of the air into an overpressure. So we have a reference pressure, and then we get a higher pressure when we kind of block the air. If we block the air totally, this will give us the higher pressure that we get on the exposed side of the building. But yes, it is a building, so therefore it's only partially blocking the wind, and there's still a little bit left in the velocity. So therefore we have pressure coefficients that tells us as a modification to the total blocking how much will be the pressure that we get on the front and also on the back sides of the building, whether the pressure coefficient is a positive number between 0 and 1, or if it's a negative number. So this we can use to kind of drive the air through the building components when we know those air pressures. So we should also consider then the wind pressures around buildings and how are the wind profiles in our landscape, and also, of course, coming close to the buildings. And there are several references for that. We can talk about an exposed climate, like in an open sea. We can talk about the countryside, in an open landscape, and that's actually where also meteorologically we have the reference as it's measured the wind velocity in 10 meters height. Then, of course, what we're interested for our buildings, we're interested in the urban areas where we have yet another wind pressure or wind velocity profile as it is. And even in the city center, it's even different again. So the wind profile is different, and also the wind velocity that we should consider as it reaches our buildings will be somewhat different. So we have this expression here, or we can see how is the wind profile for the wind velocity in open field, the meteorological measurement, as I said before, in 10 meters height. But we're interested in a particular building. So how is it with that? And then depending also on how high is the building. So we would like to know the local wind velocity coming close to our building. And there is this formula here, which says that we have the meteorological wind velocity, and then we multiply with two coefficients. One is the Greek letter kappa. You can see here depending on the landscape, what it is. And later on, I'm going to show an example where we're talking about an urbanized area. So just remember for later, kappa we're going to use is 0.43. Next, we should multiply with the height, and that should be raised to the power alpha. And alpha, you can see also in this table, in this case, for the urbanized area, I'm looking to an alpha of 0.22. So just so we can remember those numbers. With that, well, then we can calculate the pressures because we take now the local velocities we just found on the previous slide. We multiply with the density of air, with the pressure coefficient that we need for where we are on our building, and then multiply with a factor 1/2, and then we get the overpressure as it is on various places. So then we need to know the pressure coefficient, and this by empirical knowledge we can draw on such maps showing overpressures on the windward side and over the roof, and on the leeward side of the building we get an underpressure. So we get positive or negative pressure coefficients as I talked about before. The example I'm going to talk is from our exercises. One of our exercises, we talk about a building where we know it's rather big, 1,500 cubic meter, and people have made a blower door test where they have found this air change depending on the pressure difference between inside and outside of the building. So that becomes our characteristic of the building. That infiltration leak, it happens only because of wind that can come through the facades facing the wind, and also on the backward side, the leeward side. In this case, we have a meteorological wind velocity of 4 meters per second. Our building is 9 meters high. We have pressure coefficient in front of 0.7 and in the back also minus 0.5. And we are located, as indicated, in an urbanized area. We have outside, that's the number we have to use, we have outside the air temperature is 0 degrees. I'm going to go through only one of the questions in this exercise, which is one of our afternoon exercises. Only I'm going to find what is the airflow coming through and into the building under those conditions that are outlined there. There are 2 other questions which I refer to the spreadsheet where you can see the solution. But I've drawn over here on the whiteboard my building, or the building we have in the example, with all the conditions, the wind and so forth. But we're going to find the air pressure in the front of the building, facing the wind, and also in the back of the building, such that we can also, that's needed for our airflow calculations, we need to find what is the indoor air pressure also. We have the information from before with the blower door, which tells us about the leakiness of the building, but that's the result of the 2 facades, as we had from before. Gives this relationship between pressure difference between inside and outside. Then when you pressurize the building with a blower door, then you get this air change. But we need the same coefficients also, assuming that the only leakages come in our 2 facades, then we can kind of split it up in those 2 and calculate what will be the air exchange as a result of these wind pressure driven over and under pressures next to our building. Okay, I've cheated a little bit here. So first of all, I will make my calculation rather quickly by removing a piece of paper here. Then we can see that I just used the formula from before to find the local velocity of the wind just in front of the building based on the meteorological wind velocity I had from before and multiplied with the coefficients as I explained before. And as you clearly remember, the numbers are 0.43 for kappa and 0.22 for alpha. So then I can calculate the air velocity in front of the building is 2.8 meters per second. So that's the local velocity I'm now going to use in Bernoulli's equation in order that I can calculate, together with the pressure coefficients, what will be the air pressures in front of the building. Ta-da! Are you ready for it? Here it comes. The pressure in the front is, yes, the pressure coefficient and the density of air, and then the velocity. The equation lacks a division by 2 that comes from Bernoulli's equation, so I inserted that as well here. When we find that, I can see, by the way, my equation up here lacks an equation sign. That's not so important. Let me continue here without disturbing myself here too much. Then I insert the numbers as you have them from before, and that means that we get a pressure in front of the building, and everything is in SI units. So for instance, the density of air is 1.29 kilograms per cubic meter, velocity in meters per second, and the rest are numbers from the pressure coefficient and the 2 from Bernoulli's equation. So we have a pressure of 3.52 Pascal. That was in front of the building. When we use the pressure coefficient 0.7 from the front, on the back of the building we have minus 0.5 given from the exercise text. So that means also that we have an air pressure behind the building, which is minus 2.51. Okay, so now we have the pressures outside of our building. Next, we have to set up for what are the internal conditions in the building. And what I'm doing now is that I'm taking the air flow through our building component. If I look here at first to the front of the building, the left-hand part of the building, well, then we have the pressure difference is the air pressure in front of the building minus the air pressure we have inside of our building. That we should use the same equation as was used from the blower door. So we should raise the pressure difference to the power B. That was the coefficient 0.67 that was given in the exercise. So B is 0.67. we should multiply with the coefficients in front. That's the area of the building and the air transmission coefficient, K. What I've done down here is that I've divided by 2. And that is because I'm using the results that's valid for the whole house. But assuming the whole house consists of half an air change from that wall and the other half from the other wall, therefore I divide by 2 to say that this is only the airflow coming through, let's call it half of the house, the left-hand half. So that's the air pressure, the difference that drives the air on the left-hand part of the building. Likewise, I could do on the right-hand part of the building. And there, my pressure difference comes from the inside air pressure and to the air pressure on the back of the building. Both of them being raised to the power B. So now, inserting B is 0.667 and 0.23 is A times K. Then I can calculate those airflows if only I know the indoor air pressure. Then you can go and say that this equation is equal to that one, only the indoor air pressure is unknown. But also I can be a little bit smart to say that this facade is made in the same way as that, so it has the same coefficients B and AK. So therefore the result will be that the air pressure we have inside of the building, in this particular case, when there are only these 2 facades, that air pressure is the average pressure between our front pressure and the back pressure. In this case, it means that the air pressure is 0.51 Pascal. That means now I can calculate the air pressure as it is. GA is 0.23. I had from before. I divide by 2. I multiply with the pressure difference from the front 3.52 minus the air pressure inside 0.51, and that I have to raise to the power 0.67, such that in the end I get a result which is 0.24 kilograms per second. Then I found the airflow through that facade, and that should then also be the same result I get if I insert from the right-hand facade. So this is the air change. That is what comes in, should also leave the building, so the same rate of airflow. That completes question A in this exercise. Next, you can go for yourself or check the Excel sheet how to calculate the heat flow that this causes, this air change. And also there's a question about how should the construction be changed in order to have an air change rate, which is 0.2 air changes per hour. But this I leave for yourself to study. So thank you for listening to this.